Hi, everybody. I am going to go ahead and jump into protein structure and higher order protein structure. So far, what we've discussed in class is we've discussed your primary structure, which is your polypeptide sequence directed from the N to the C termini. Then we've discussed secondary structure, where we talked about kind of those local structures, which are stabilized by hydrogen bonds. The examples for your secondary structures are the alpha helix and beta sheet and beta turns to a little bit lesser extent. What we're going to be doing now is we're going to be venturing into like I said, higher order. And we're going to be getting into your tertiary and quaternary structure. Basically, how does a completed polypeptide chain, how does it contort itself in 3 dimensions? So your X, Y, and Z plane. Now, where we kind of left off previously was looking at this table right here, which was our Chou-Fasman scoring for secondary structural propensities. And if you look at this, this was just showing every single amino acid was given a score back in the 1970s as to whether it was likely to fall into an alpha helix or a beta sheet, or not fall into, but be found in an alpha helix or a beta sheet. Now, what's significant about this is that this was basically data that was collected from protein structures of the day, and each amino acid was kind of looked at as, is it found in an alpha helix, is it found in a beta sheet? And based on its frequency and presence in those different structures, it was given a score. Now, ultimately, the value of this is this gives you a means to predict um, based solely on the primary structure of a protein, whether or not you're going to have a alpha helix or a beta sheet form. Now, the value of this is basically gives you the power to, like I said, look at the primary structure and say, yes, an alpha helix will form, or no, an alpha helix will not, but a beta sheet will. Now, this is great and highly valuable because it ultimately is a kind of a direction of, and all right, here's some of the example rules. I'm not going to be testing you over this on this third exam, but it gives you a direction to look at, well, what can you find out from primary structure? What's the value of knowing that? Is it kind of uh, let's see, is it interactive? Is it valuable data, or is it pretty, I don't know, trivial almost? Like, oh, neat. And this was the first instance where you learn that no, it's not simply trivial information. That information is highly valuable because it tells something about what's to come. So now let's go ahead and transition to our discussion of tertiary structure. The tertiary structure is the folding of a polypeptide chain in 3 dimensional space, and this is concerned with an arrangement, all of the atoms in a polypeptide chain, where they are with respect to one another, and where they are with respect to an X, Y, and a Z plane. So the 3 dimensional fold or 3 dimensional structure of the protein. Now, the conformation or organization of this, this word conformation, it's interchangeable for shape, fold of a protein. The conformation of the side chains and the prosthetic groups are included, as well as the packing of helices and sheets. So this prosthetic groups, think about that as, well, the way that you think about a like arm prosthesis or a leg prosthesis. It's something that is more or less helpful for a protein structure to carry out a particular function, or sorry, it's beneficial for a person who needs a prosthetic limb or something like that, that they have it, because it gives them the mobility and ability to walk or pick something up. A prosthetic group in protein terminology is more or less the same thing. It's a chemical modification or chemical group that is associated with a protein's structure. So your protein structure is just the polypeptide chain, all of the amino acids. A prosthetic group would be something that is not necessarily amino acids and is added to that protein after it's been produced. So the formation of the tertiary structure is primarily determined by interactions. This is a very important thing. Interactions of the amino acid side chains with each other and the backbone atoms. So I want you to think about this as the different levels of protein structure. Primary structure is stabilized simply by covalent bonds. Secondary structure is stabilized by backbone hydrogen bond interactions. Tertiary structure is how do the different R groups interact with one another, and how do they interact with backbone atoms? Now, one important thing to think about is, let's say you have an amino acid like serine. Serine is an amino acid that can form hydrogen bonds. And if that's serine, or if a serine forms hydrogen bonds with another serine, well, that would be two R groups interacting with one another. And so that would be a part of the tertiary structure. That same serine is also capable of forming a hydrogen bond with the polypeptide backbone of a protein. And that too would be tertiary structure, or designated as a part of the tertiary structure. So keep in mind that it's what are the not just the types of interactions, but instead what are those kind of what atoms are we talking about? If we're talking strictly about backbone interacting with other backbone atoms, well, that would be your secondary structure. Backbone interacting with R groups, that's your tertiary structure. So an important distinction there. So, like I said, it's now relatively commonplace and fairly easy to predict the secondary structure of a protein, but predicting the tertiary is a lot more difficult. Now, the quaternary structure, that next level of protein, or next level protein shape and organization. Well, there are many proteins that consist of more than one polypeptide chain. Those different polypeptides, for instance, or those proteins that have multiple polypeptides, those different polypeptides are subunits. For instance, the protein hemoglobin. Hemoglobin is made up of 4 distinct polypeptides. Those 4 distinct polypeptides are also known as distinct subunits, or monomeric units. So the individual subunits associate in a specific organization or a specific way, specific geometry for that protein, and this is known as the quaternary structure of a protein. Subunits interact through non-covalent interactions. Proteins with more than one subunit are called oligomers, and those oligomers are examples of those oligomers are dimers, trimers, tetramers, pentamers, hexamers, heptamers, octamers, nonomers, decamers, and it goes on from there. Now, here are some examples of different proteins and what they consist of. One at the bottom that I would like to highlight, which my mouse has escaped me at the moment, and I'm going to plug it in on this side of the computer so that works. Which one are we talking? Yep, there, that's the one. This protein at the bottom, Titin, this is the largest known protein, and it has a total of 34,350 amino acids. Now, the size of that protein, each one of those amino acids is approximately 110 Daltons. It's 3,816,188 Daltons. So, as an alternative to that, we've got an enzyme known as glutamine synthase. That's an enzyme that's in E. coli that is involved in synthesis of the amino acid glutamine. It is 12 different polypeptide chains. Those 12 polypeptide chains add up to a grand total of 5,616 amino acids for a total mass of 621 Daltons. So proteins are composed in different ways. They're composed of multiple subunits in different ways. And the overall molecular weight of those proteins is going to vary considerably. But these are just some examples. Now, when we talk about proteins and the shapes that they form, and this is kind of an offshoot of tertiary quaternary structure discussion, but proteins will form either and be categorized or classified as either globular or fibrous proteins. Now, globular proteins are proteins which are more or less shaped in a slightly spherical shape. Now, that's not to say it's a perfect sphere or anything like that, but instead there's a amorphous, like blob type of shape to them. Compare that to fibrous proteins. And I personally think that, or I personally think about fibrous versus globular proteins, and I kind of define a fibrous protein first and then say anything that doesn't have this shape is a globular protein. So fibrous proteins contain polypeptide chains organized approximately parallel along a single axis. So proteins that have a kind of rigid shape like such, this would be an example of a fibrous protein. And I think that this representation is helpful. This piece of paper is helpful because it shows that this fibrous protein has like structural integrity to it. It's not going to really bend or anything like that. Now, if you compare that to unfolding this fibrous protein, something like this. Well, what's the shape of this? I don't know. Kind of looks like a, well, it's like a sphere that someone flattened and then stretched a part of it out. That would be an example of a globular protein. So fibrous proteins, the key with respect to fibrous proteins is that these are polypeptide chains, or multiple, in most cases, multiple polypeptide chains organized parallel to a single axis. So they're working along a single axis. Now, globular proteins arguably are the more interesting ones because your fibrous proteins, those are going to be like collagen, actin, the structural proteins, the proteins that give cells some structural integrity. Globular proteins are generally going to be the ones that do something, something outside of kind of holding things in shape. Instead, your globular proteins are going to be your enzymes, the ones that bind to sugars and break them down. Now, globular proteins can contain only alpha helices or only beta sheets. They can contain a significant number of alpha helices and beta sheets. So they can be very narrow in terms of what they structurally are about, but also they can have some kind of flexibility to them. The large number of hydrogen bonds in the secondary structural elements act to neutralize or stabilize the polarity of the peptide backbone. So the large number of hydrogen bonds in the secondary structure basically keep that protein's overall extremeness, meaning number of positive versus negative charges and no charges whatsoever, kind of stabilizes those. Now, in a globular protein, most of your hydrophobic amino acids are going to face the interior of the protein and interact with one another. Think about that. Whenever you have a linear polypeptide chain, or sorry, when you're looking at the primary structure of a protein, so just looking at the amino acids that compose that protein, if you can say amino acids 10 through 15, for instance, are all super hydrophobic, and examples would be something like leucine or valine. Leucine or valine are in there, and phenylalanine. Well, those amino acids are probably going to be packed into the center of this globular protein. So they're going to kind of, if you think about a protein structure as similar to the Earth or something like that, those are going to make up the core of that protein. Those hydrophobic residues are going to be packed deep in there. Whereas your polar residues, your hydrophilic amino acids, are going to be kind of on the surface. Now, many polar charged residues, so your polar charge would be your aspartic acid, glutamic acid, lysine, arginine. They're going to face the outside of the protein and interact with the solvent, interact with the environment. Now, those that are in the interior participate in hydrogen bonds or ionic interactions. So they can be found in the middle, but if they are, they're going to be involved in ionic interactions. So think about this as Polar charged residues can be in a couple of different places. Your hydrophobic or your non-polar residues are probably just going to be on the interior. Now, your polar non-charged residues can be found throughout, but if in the interior, they're going to participate in hydrogen bonds. So examples of those would be asparagine, glutamine, serine, threonine, tyrosine, sorry. Those are, and histidine, those are going to be proteins, or sorry, amino acids that are going to stabilize hydrogen bonds or participate in hydrogen bonds. Oof, no, sorry. The interior of a protein is more analogous to an organic solvent, thus the pKa's, the ionizable side chains, can be interrupted or can be altered a little bit, perturbed. Some examples of these, here's your pKa values for a couple of different amino acids and how they change based on a particular peptide. So what this is showing us is the pKa values of ionizable side chains in a series. So basically what this is this is looking at data from a synthetic polypeptide. This polypeptide was seen at the bottom, that first star or that first asterisk reads pKa value of an AAXAA peptide with the termini blocked. Okay, so what somebody did was they synthesized this polypeptide where the amino acid in the middle was aspartic acid. Okay, and then it was also glutamic acid. And what they did was they found that the pKa value ranged from 3.9, or sorry, the pKa average with a bunch of different titration curves that they did. They found that it was as low as, I guess that would be 2.3 and as high as 3.7. So that pKa average tells us what experimentally was observed when this synthetic polypeptide was synthesized. And so what I really want you to take away from this is not the specific numbers, but instead I want you to think about, okay, histidine, for instance, has a pKa of 6.5, but what are the amino acids that are surrounding it? Is it and the amino acids that surround or that are adjacent to one specific ionizable residue, those are going to display the inductive effect and can cause that pKa value to shift, either go down or go up. So that's really what I want to show here. And basically, it's a way of saying that some amino acids, for instance, aspartic acid, yeah, aspartic acid is highly likely to participate in ionic bonds, but that doesn't mean that it can't participate in hydrogen bonding. It really just depends on what the amino acids up and downstream of it are based on this. Now, here's some examples of globular proteins and really just intending to display the dynamic differences between them. If we look on the left, we have this protein known as avidin. Top middle, we have myoglobin. Bottom middle is ribonuclease T1. And to the far right, we have an enzyme known as carbamoyl phosphate synthetase. Now, what I want you to do when you look at avidin is I want you to see those kind of turquoise or teal arrows. Those are all beta strands. Now, those beta strands assemble to make anti-parallel beta sheets. Now, the green ribbon outside of that, I think that there's a tendency for people when they look at a protein sequence or look at a protein's 3D structure, which is what we're looking at here, is they say, aha, well, there's my beta sheets, for instance. Therefore, everything else must be an alpha helix. That's not correct. And so don't be tempted to do that. If we look at avidin, the colors that I see with respect to my ribbons or my polypeptide sequences are teal and green. Well, teal, alpha helices. Green, that is simply a random coil. So that's not defined or that's not tied down as a alpha helix. That makes up a random coil. Now, if we look at myoglobin, that's a ton of alpha helices, and some random coils. If you look at ribonuclease T1 in the bottom center, it's kind of tough to tell, but if I use my annotate tool, you can see right here, right here, 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 and here. I've got kind of arrows. So I've got some beta strands in there, and then on the left-hand side of the structure, I've got an alpha helix. So this is a combination of alpha helices and beta sheets. Then if you look at carbamoyl phosphate synthetase, well, that's a complex protein where we've got tons of different alpha helices and beta sheets going on. So your globular proteins are going to, by comparison to globular versus fibrous protein, your globular proteins are going to have structures that are much more complicated than, say, a filamentous or a filamentous protein. All right, well, I'm going to go ahead and stop there, and I'll continue on in another video.